So we will have the three presentation, and the first one is from Keith. So yeah, feel free to start, Keith.
Okay, thank you, Edwin. Okay, so my name is Keith Ord. I was a professor at Georgetown sometime in the last millennium. This particular research is motivated by the M4 competition. The M4 competition basically took a set of methods and then ran through a lot of series to see which methods performed best in terms of creating prediction intervals. This work is taking a different slant in that we're looking at selection of a model for a single series and saying, what do prediction intervals tell us that would help us choose a model which may be different than the information we get from the usual approach of fitting a model and choosing the best fitting model, or possibly the best set of point forecasts. So the focus is on prediction intervals. So start with a little bit of background and then comparisons of prediction interval methods, what was in M4 and another approach. We'll then go on to look at how these results might be used in model selection, and I'll do that using a case study using the well-known Box-Jenkins Airlines series. Then we'll conclude with some directions for future research. So just by way of background, a model is a metaphor of limited applicability, not the thing itself, or as George Box famously put it, all models are wrong, some are useful. So we're looking for something that gets the job done rather than is proving perfection. Why do prediction intervals matter? Well, often people tend to work with point forecasts and ignore uncertainty. And as Walsh said in a recent article, rather than trying to be right, how about if you could be less wrong over time? And prediction intervals help you to do that. In the special issue of the IJF relating to the M4 competition, Fry and Brundage said, in fact, for some capacity problems, we find that it's often more important to get the upper quantiles correct than to actually get the point forecasts correct. You could think of stocking decisions in retail sales, or the volume of water in a dam, or whatever. The upper interval is what's important. And you can also think of situations where the lower interval might be important as well. So the M4 competition is probably familiar to most people, and I won't spend time on that. For those who are not familiar with it, there's a whole issue of the IJF devoted to the competition, its results, and a detailed discussion. In the course of that competition, they presented a method for comparing prediction intervals known as the mean scaled interval score. And in essence, that's combining a penalty for the width. A very wide interval is bad. On the other hand, missing the observation is bad. So the MSIS, which I've split into two pieces, the upper limit is the distance between the upper limit and the point forecast. That's the upper width, and then a penalty if the observed value exceeds the upper limit. The penalty is proportional to the amount of the excess, and the 2 upon alpha relates to the prediction interval you're looking at, 95%, 99%, 1 minus alpha being the probability attached to the prediction interval. Same thing for the lower limit, except obviously you go out in the other direction. And then the MSIS is simply the sum of those two. So you could look at the tails separately, or you can look at them in combination. In thinking about it, an alternative measure can be defined following in the context of an information criterion. So we can look at the marginal probability for each forecast going 1 through h steps ahead, and then look at the log of the marginal density function, and taking the conventional -2, which is convenient when you're looking at it in the normal context. Clearly, these successive terms are not independent, but they're not independent in the MSIS either. So set up like this, a smaller k is better. You can ignore constants like a √2 pi in the normal case. You're just comparing across measures. One of the advantages of the k measure is you can use it to compare directly across different transformations. So you could have a linear form, square root, log transform, whatever. Also, you're not tied to a particular level of confidence. So it's not a 95% prediction interval or 99%, rather you're defining it across the entire marginal distribution. Just as we split the MSIS into upper and lower tail measures, you can do the same with this k measure by attaching the signs of the error terms. And you can look at the ratio or the log ratio of these two. If the tails are in balance, the log ratio will be near 0. It'll be positive if the upper tail is too wide, negative if the lower tail is too wide. So we have a series of measures for evaluating prediction intervals. Now let's look at the case study, the famous Box-Jenkins airline series, which, as we all know, has an upward trend, a strong seasonal pattern, and increasing variability over time. So taking account of those three factors, Box and Jenkins proposed the ARIMA 011, 011, 12 monthly model, which is widely known as the airline model. And because of the increasing variance over time, they recommended the use of a log transform. Way back in 1973, Chatfield and Prothero suggested the log form might be an overcorrection, but they were kind of shouted down by the faithful. Over time, people have suggested other transforms. We'll just take a cube root as an example. In order to contrast the airline model with something else, we'll look at an ARIMA model which replaces the 011 by an AR term, but retains the moving average structure for the seasonal component. So what happens when we fit these? Well, looking at the root mean square errors in the transformed measures, you can see that each time the alternate model has a slightly lower value, but it also has an extra parameter. So basically, it's pretty much a wash. So in terms of the point forecasts, it's not really anything to choose. But when we look at the diagrams, a different picture emerges. Here's the log transform and 95% prediction interval. You can see the interval is way too wide compared to the forecast in brown and the actual values in blue. The lower interval is also too wide, though not as pronounced as the upper interval. When we look at the linear case, the balance goes the other way. The lower interval is wider, but again, they're far too wide. And the cube root case, again, far too wide. When we look at the alternate model, the intervals are much narrower. In the log case, again, the upper tail is a bit too high. The cube root pretty much hits the upper limit right on the button, but is deficient on the lower tail. But they're very much tighter. That's clear, whichever model you choose. So what do the measures tell us? Well, if we look at the bias, the mean forecast error, the bias in the log predictions is extreme and negative. The observed is way less than the expected. If we look at the mean absolute forecast error, the same pattern applies. There's not much to choose between the linear and the cube root, or between the airline and the alternate, but the log model is clearly inferior. If we look at the measures for the prediction intervals, the linear model does best at the lower tail. The cube root does best at the upper tail. In aggregate, the cube root alternate model has the lowest value for the MSIS. And the airline model is pretty similar across both the models, across the linear and the cube root. Again, the airline model is inferior and markedly inferior for the alternate model. We can also look at the failure rate. So the failure rate ought to be of the order of 2.5%. It's pretty much on for the upper tail, but deficient for the lower tail. When we look at the airline model, the intervals are so wide that they never fail. Make the intervals wide enough, you're never going to miss, but you don't not get much in the way of information. So on balance, it would appear that the alternate model is better and the cube root transformation is to be preferred, but certainly the logarithmic model is not to be preferred. If we look at the alternate measure that was proposed using the densities, then you can look at the values and you can see that the cube root, the alternate model, is marginally better, though there's not a strong difference there. The airline model is slightly better in the linear case. When we look at the log ratio, the airline model and the alternate model are both deficient in the upper tail, whereas in the cube root case, they're deficient in the lower tail. The logarithmic model is way over in the upper tail, as we saw from the diagram. So putting all of that together, you can see that the airline model is clearly deficient when we're using the log transform, and that in general, the intervals tend to be too wide when you're using the both seasonal and regular differences. The cube root doesn't correct completely, and I purposely didn't attempt to optimize that because I wanted to emphasize the performance of the different measures.
Okay,
So
sorry
what-
to interrupt. You have 5 minutes left.
5 minutes. Okay, thank you, Edwin. So what can we conclude? Well, first off, choosing a forecasting method based only on point forecasts may give poor results for interval forecasts. And if the interval forecasts are important to you in terms of restocking in the retail trade or whatever, then choosing just on the basis of the point forecast could give you poor results. So width versus coverage is important. If the interval is too wide, it's going to be meaningless. The K function in particular, or the MSIS, will take care of those issues. Performance in the upper and lower tails could be quite different. What's important in the current application? Are you concerned about the point forecast, about the upper tail, about the lower tail? Looking at the measures of the interval forecast helps you to decide what's important and what's a valid, useful measure for the thing that's important in your case. Over-differencing, typically over the years, we've said that doesn't matter too much. And in context of point forecasts, that's probably true. But as the pictures show, over-differencing gives you prediction intervals that are excessively wide. And log transforms are very appealing when considering point forecasts, but they may lead to overly wide prediction intervals, particularly for the upper tail. So if the upper tail is important, you've got to be very wary of logarithmic transforms. This is just a preliminary dipping the toe in the water. There's all kinds of questions. Which measures should we use? Is it okay to rely on normality, or should we be using other distributions, or should we be using bootstrap methods? Should we be using loss functions? So in the context of retail sales, we'd be looking at a trade-off between being out of stock as opposed to holding excess stock. And if we're looking at automatic packages, how do we combine performance over the point forecast with performance for the interval forecast? Some kind of combined function would appear to be relevant. So that's all I got, and hopefully there's time for a few questions. Thank you.
I actually have a quick question. So in the loss function you show, like, did you consider like some typical loss function like pinball loss, things like that? Or like
No,
yeah.
That's something that would be very interesting to look at. I really didn't, I said I'm really just scratching the surface. There's a variety of directions one could go, and choosing a loss function which reflects the important features of the particular study is clearly an important direction to go.
Okay. All right. I think we have another session from Eric. So feel free to start your presentation. This is your time.
Okay.
And thank you, Kip.
Thank you.
Thanks, Edwin. Thanks, Steve. Okay, so let me just share it real quick. Okay, can you all hear me and see the screen?
Yeah,
Yep.
we got the screen.
Okay. Okay. Okay, so thanks everyone for coming. Okay, so today I'll be giving a small talk about estimating interval forecasts using pruned ensembles. Basically, we are talking here about a bootstrap aggregation algorithm, which was originally designed to produce point forecasts. And we extend the use of this bagging algorithm to generate the prediction intervals as well. And we also come up with a strategy to prune certain bootstraps of this in this algorithm, so that the final result, so that the final prediction interval is sharper and more accurate usually. Okay, so I'm Eric Meira. I'm a postdoc research fellow at Pontifical Catholic University of Rio de Janeiro. My now supervisor, I would say, the mentor, is Fernando Serino. He's also co-author of this work, which has been recently published in the Energy Journal. And we also have Lilian de Menezes. She's a professor at City University of London, Bayes Business School. Okay, so our motivation, well, okay, the importance of reliable energy planning cannot be overstated. I mean, we all know that the importance of having reliable forecasts of energy consumption so that electricity supply can be optimized, for instance. However, developing an energy plan is not straightforward. We are talking here about energy supply time series. That's the point of our topic today. So that's why I'm talking, just giving a little brief motivation on the importance of reliable energy planning. The major concern, which is inherent to most decision-making within the management of power system, is the uncertainty of the future outcomes. In this connection, predictions of electricity supply are essential for minimizing energy costs, security capacity, providing high quality services, and so on. Perhaps most important than having reliable point forecasts, I would say exactly meeting the consumption, is having reliable prediction intervals of this consumption so that you can optimize your future supply. Not only these prediction intervals, they help you to reduce the random variation in single value time series forecasts, but they also minimize the risk inherent to decision-making within the management of these power systems. So in this present study, as I previously outlined, we extend here the use of this particular algorithm named after bootstrap aggregation to generate prediction intervals as well. Basically, we are combining bagging algorithms with time series methods, namely ETS models, and pruning strategies which are capable of future selection. So we are going to discard some of the forecasts in the bagged ensemble to finally aggregate these remaining forecasts and produce the final prediction intervals and the final point forecasts. So this approach contrasts with previous proposals for BI generation in three main ways. First, because it delivers prediction intervals without the explicit need to generate the point forecast. In most cases, a two-step process is adopted. First, you generate the point forecast, and then you come up with a strategy to build the prediction intervals based on the results of your point forecast. Basically, we're talking here about simulation, or maybe using a normal distribution to simulate the prediction intervals based on the value of the point forecast and so on. We show here that our method can generate these prediction intervals independently. The second concerns the generalization and robustness of the method, because given the hybrid properties of this ensemble approach, different stylus effects of the time series can be addressed, such as nonlinearities, stochastic components such as trend and seasonality, and so on. Finally, we also show that the prediction intervals, they are unlikely to increase significantly over the forecasting horizon, which is usually another characteristic of most previous proposals for PI generation. This is particularly important for decision making within the management of power systems, because companies can only address a certain limit of uncertainty, given the high costs involved in energy storage systems and capacity management, for instance. So this is just a brief overview of how bagging is usually conducted for point forecast generation. So first you have your original series, you come up with a transformation such as the Box-Cox transformation. You decompose this transformed series into 3 components, namely the trend, the seasonal component, and the remainder. You come up with a bootstrap method to generate the replicas of this remainder. And then you invert the transformation and add all these, components again after the replica generation, and invert the transformation so that you have the bootstraps of the original series. Basically, we are talking here about J series. So you have the original series plus J-1's replicas of this original series. Then you come up with a forecasting method for each of these series independently. And you aggregate all these forecasts according to a strategy that could be a mean aggregation or median aggregation. We are going to be using the median in this paper here to generate your final forecasts. In this way, some authors show that you can address several sources of uncertainty related to the time series, such as data uncertainty, model uncertainty, and parameter uncertainty. Just a brief overview, we are going to be using the ETS algorithm to generate our forecasts here for each of the bootstraps of the original series and also the original series. So basically a brief overview of how ETS algorithm works. It's basically a selection algorithm. You test by default 15 ETS model forms. You could test up to 30, but the default is to test 15 ETS model forms, and you select the best fit model by minimizing an information criteria. For instance, the archaic information criterion with corrections. So basically, we will be using this algorithm, for instance, 100 times, if we are talking about an ensemble of 100 time series, the original time series and 99 versions of this series, artificial series, which share similar stylized facts as the original series, but have different observations. They are slightly different from the original one. So that's the idea of bagging. So we'll be using this algorithm 100 times because we're using here 100 time series in the bagging algorithm. So in a nutshell, what does bagging do? As I mentioned previously, you have the original series, you generate the replicas of this series, you use the ETS algorithm, and you generate the J point forecast. So here we're talking, for instance, about 100 point forecast, and you aggregate all these forecasts using the median to have your final results, which is the final point forecast. So beside aggregating the point forecast, we will be also aggregating their prediction intervals, namely the upper prediction interval limits and the lower prediction interval limits. This is possible because regardless of the resampling approach, I mean, the bootstrap strategy to generate the replicas, for instance, all point forecasts, they are generated via the ETS algorithm with their corresponding prediction intervals generated at a certain predefined coverage level, for instance, 95% theoretical coverage level. And the second step after the generation of the upper and lower prediction intervals, we'll be conducting a pruning strategy to eliminate some of these upper and lower prediction interval limits. So the idea here is to look for deviant behaviors in these prediction interval limits by compare these limits with the other generated limits. So we have, for instance, in this ensemble, 100 point forecast. So we also have 100 upper prediction interval limits and 100 lower prediction interval limits. We'll be comparing the upper prediction interval limits, this set and we'll be conducting an outlier detection in these prediction interval limits, so that you'll be left with J minus J1 upper prediction interval limits. So for instance, if once you had in the original ensemble 100 limits, now you'll be left with 85, for instance. And the same procedure, the same outlier detection is conducted in the set of the lower prediction interval limits. So we'll be left with J minus J2 lower prediction interval limits suggested to be further aggregated using the median or the mean, for instance. The second step is the removal of the outliers. So the point forecasts, which were associated with the upper prediction interval limits that were discarded in the first step, they are going to be discarded as well. So at the end, we'll be left with J minus K point forecast, J minus K upper prediction interval limits, and J minus K lower PI limits. K is basically the sum of J1 and D2 minus their intersection, because there will be cases in which the same point forecast and associated limit is suggested to be discarded when conducting the outlier detection in the upper prediction interval limits and in the lower prediction interval limits as well. So in the end, for instance, let's say we had 100 point forecasts in the ensemble, we are left with 80 point forecasts in the final ensemble, and also associated prediction interval limits. For a practical view of how this is conducted in practice, let us consider here the US monthly energy supplied in gigawatt hours. Here in the first graph, we see all the observations in slate gray. The train set here is January 2000 to September 2018. Test set is the following 24 observations from October 2018 to September 2020. And here in the second graph, we are looking at the final results of the MBB. MBB stands for Moving Blocks Bootstrap, is basically a bootstrap algorithm to generate the replicas when I showed the bagging algorithm a few slides earlier, and pruned bagged ETS. So basically we're talking here about the bagging ETS strategy after you conduct the pruning strategy to eliminate the outliers, right? The final result is the forecast and prediction intervals in blue, and in dash red, we are looking at the actual values. I consider particularly this result as a good result, since we are talking here about 24 steps ahead forecasting. And there was also the COVID-19 period, specifically the months of March and April 2020, which were critical in terms of lockdown measures and so on. So basically we were able to generate a good prediction intervals, which covered almost all observations throughout the forecasting lead time, and left with only a few, basically one or two observations which were below the lower limit of the prediction interval. And here's just a comparison of how, when we conduct pruning, we are also able to improve the forecast of the point forecast as well. For instance, the maze of the pruned bagged ETS was throughout all this forecast lead time was 4.03, and without pruning it would be 4.13, for instance. So this is how pruning works in practice. Where in the first graph, the first graph shows the remaining upper PI limits in gray, and the outliers, the upper PI limits which were suggested to be removed and were further discarded in red. The second graph shows the point forecast. So basically what we suggest to be removed in the upper PI limits were the same point forecasts in the second graph. So we eliminate the upper PI limits, and we also eliminate the point forecast.
Sorry to interrupt. Eric, you have another 5 minutes.
Okay, yeah. So just to show an empirical investigation of the pruning practice, we consider here 16 monthly time series of total electricity supply from 16 countries. And as I mentioned earlier, the test set comprised 24 observations, so the forecast lead time 24 steps ahead. And we evaluate the accuracy of the point forecast according to the average rank and box plots of the SMAPE and MAZE. And we also consider the average rank and box plots of the MSIS, which is a measure of accuracy of the prediction intervals. I cannot delve into details here, but it considers not only, it penalizes not only the width of the interval, but also the moments in which you had observations which were below or above the prediction interval. And finally, we compared our methods with some benchmarks and recent bagging routines. So basically, we're talking here about, we compared with ETS, ARIMA, and additive hot winters. And we consider recent bagging routines, the bagged ETS by Bergmeier and others from 2016, and the bootstrap model combinations by Fotis Petropoulos and other authors, 2018. These are our final results. So we consider here 3 different resampling procedures: the MBB, moving blocks bootstrap, the CBB, circular blocks bootstrap, and the LPB, the linear process bootstrap. And in every occasion, the pruned approaches deliver better results in terms of average SMAPE, average rank SMAPE, average MAZE, and average rank MAZE. Also, all the bagging approaches pretty much presented better, more accurate values than the benchmarks. The same can be noted for the for PI evaluation, predictor interval evaluations, in which we consider the average MSIS under different theoretical coverage levels, ranging from 80, 85, 90, and 95. We also consider the whole range from 80 to 99% coverage levels, and up to the 97 theoretical coverage levels, we had the pruned bagged ETS and the bagged ETS providing substantially better results than the BMC and the ETS. The 98 and the 99 theoretical coverage levels, given the large width of the bootstrap model combinations, the resulting values of the MSIS were slightly better than in the other cases. Just a brief overview of the box plots as well, since my time is running out. I have 2 more minutes, but pretty much the same situation that I showed earlier in terms of average and rank and average rank, you see also in the distribution of the box plots. And finally, the performance per country as well. We see the MBB pruned bagged DTS forecast, which was by far the best methods when compared with the other bagging approaches. So the prediction intervals of forecasts are highlighted here in blue, the actual values in dash red, and these are all the countries considered. So we pretty much covered all the actual values. Sometimes given the lockdown measures of COVID-19, the consumption were a little bit lower than the lower limits of the prediction intervals, but the results are fairly good considering that we are talking here about 24 steps ahead forecast lead time. So following the philosophy of wisdom of the crowns, we propose an ensemble approach to generate accurate, precise forecast and prediction intervals. The methodology is adequate to and robust to forecast electricity supply over both short and considerably long lead times, as well as during periods of economic stress. As methodological extension of this work, we could be investigating other decomposition schemes and bootstrap algorithms. And for country-specific assessments, a hierarchical disaggregation approach could improve the final forecasts as well. Thank you for your attention. Be happy to answer some questions if there's time yet. That's it.
I think there is one quick question. I think we can do that basically it is about the groundness of the proposed PI method. Do you have any theoretical asymptotic, I guess, results about the coverage?
Okay, let's go back. You mean here the asymptotic behavior of okay, so pretty much all I can say was when you consider high coverage levels, as I mentioned earlier, there's a difference between the pruned BACD test and BACD test. They start to delivering, you would say, not the best results when compared to the BMC, for instance, because of the length of the width of the interval. Since the idea of pruned specifically is to reduce the average width of the final intervals, if you consider high coverage levels, these methods, they are sometimes not prioritized, you'd say, and they might not cover all the observations if we are talking here about a high theoretical desired cover levels. Yeah, I don't know if that was the point here, but as for what I understood.
I think we are about to cut off for this one. So thank you, Eric, for the presentation.
Thanks.
All right, so in the next session, I'm gonna present about ORBIT, which stands for the Object-Oriented Time Series Forecasting. So just a quick introduction of myself. I'm a data scientist from Uber. I'm the lead for this open source Python package time series modeling project. So last year we present some preliminary version of ORBIT. So this time, instead of going through the particular model like LGT, DLT, I have gone over last time, I'm going to deliver like a current status of this open source package and an overview was the use cases of this package. A little bit more background. So we are a group of data science originate from the and folks are already working in Facebook, and that we have some use cases besides the internal use case. We also have some use cases from Pinterest and Facebook. And for more details, feel free to check out our GitHub page, documentation, and also the blog post. So the structure of this talk will be into like 5 sections: the motivation, introduction, the package design, and the performance of the model. And we will dive into some hands-on section at the end. So first, why do we choose Bayesian methods? So that's back to the some story behind why we kick off this open source project. There are a lot of use cases we need to, besides the time series modeling, we need to do some robust regression analysis. Especially, we need to make decisions based on those like regression analysis. For example, like treatment effect, some causal analysis, time series synthetic control, and some like demand planning, demand forecasting, and then with the planning with some external factors, something like that. So Bayesian just come to mind in a very natural way. It helps us to make decision naturally by estimating the variation of the prediction as well as the parameters. And there is we recently published a paper built based on ORBIT called Bayesian Time Varying Coefficient Model with applications to marketing mix model. And we are going to present this in at KDD in the upcoming August, mid of August. So feel free to check it out, this paper, if you're interested. So then one step forward, we noticed there are a couple of packages in the industry, especially like the probabilistic forecasting APIs such as Stan and Pyro doing some Bayesian modeling. But what we noticed is that for those APIs, it may take the users some time to understand the syntax and to set up the building blocks, and let alone to understand some of the knowledge. For example, like how to approximate the posterior, for example, like SVI. You need to pick your approximation like with the some probabilistic distribution, things like that. So it's not that intuitive for the analyst or some business use case users. So that is the motivation from us. We basically try to bridge the gap between those powerful APIs to an end-to-end goals for a business problem. So our focus on the package is to structure the workflow as a Bayesian time series model into a few steps, mainly include picking the model, prior configuration, fitting the model, and then extract the posteriors. And finally, we provide some diagnostic tools so that we can iterate very fast on model deployment, development and deployment. And this is just a interpretation from our team. So don't be nervous if you disagree. So basically, on the one hand, we have this Pyro, Stan, PyMC3, TensorFlow probability, which provide a very generic, general way to do probabilistic modeling. While it is research friendly, but it made a lack of some quick implementation for the business problems. On the other hand, we have Prophet and BSTS. They are model based, so they can implement a model very quickly. However, they lack of extensible design for, like, if there are researchers come in, I want to like develop a new model, it lacks of those kind of facility to do that. So Orbit try to make a trade-off between these two types of packages to, like, first we provide a quick implementation for analysts to meet their business needs. Meanwhile, we provide some extensibility of the code so that we can keep developing new models, and we use some of the procedures we already developed for Bayesian time series modeling. So in high level, there are 6 advantages I will summarize for Orbit: ease of use, flexibility, interoperability, object-oriented design, workflow support, and high performance. So we will have a follow-up slide for each of these points. So because we are running out of time, let me just skip some follow-up here and dive into the following slides. So for ease of use, we designed the package such that each command line stands for a major step. So you can see that from initialization to getting the insights, all you need is these 3 steps plus the to get the outcomes extracted. First, we initialize the model, and then we have another step to feed the model with the train data frame, and then we call the prediction for the test data frame, and then you can get the data. You can get the results from the procedures. So this, with this, it will be very convenient for the business users to follow this initialize, feed, and predict steps. Next, we provide some flexibility for the modeling. For example, we allowed different prior distribution selections, and want to highlight that we also provide some bounds for the distribution. For example, like a truncated normal from the positive or not negative side. And also the users can control the confidence of their priors, such as a weak versus a strong informative prior. And then we provide different algorithms of sampling. For example, like we have MCMC and SVI supported. And with that, we also support different probabilistic programming APIs such as Stan and Pyro, where MCMC or NUTS is implemented in Stan and SVI is implemented in Pyro. And finally, for people who are interested in point estimate, we have the maximum posterior, and also we have the other aggregations such as the mean or median from the posterior distribution. So we try to enhance the interpretability by providing an optional decomposition from the models, where when the model support decomposition, we can output the prediction. We can output the like not just the prediction, but also the decomposition, including like trend, seasonality, and regression. So that hopefully can inform the users which part of the model can be improved. Then we also spend a lot of effort to design the package such that it is extensible and also like reusable for the main procedures. So the way we do that is to have this multi-inheritance design. We have the two core class, which is the estimation template and also the base model. So on the one hand, the estimation template will take care all the reusable process, such as how we organize the posteriors, how we should handle different situations when we have like MCMC versus SBI, and how what are the standard pre and post data processing for a time series, such as getting some boring mean and standard deviation, and some useful statistics for some data-driven prior. On the other hand, the users need to provide the base model, which is another abstract class, to distinguish a model from another, such as by defining such as the likelihood functions, and also the how we should do the prediction and provide the prediction intervals. So with these two abstract, it ends up to be a concrete model to be used in the implementation. So another look of the design is we with the initialize, fit, and predict style I mentioned. Basically, the estimation template take care of some default priors, some data-driven priors, and also some initialization with the some point for sampling. And then the users can add their own validation like a data pre-processing. And then from in the feeding process, we provide some default pre-processing. As I mentioned, the data-driven priors, some other useful metadata extraction, and then the user will provide their filters, which includes the likelihood function and also other sampling procedures. And then in the prediction phase, it is similar to the fitting phase. So the users need to provide their own logic how to do the prediction, and then we provide some tools to help on some reusable procedure like pre-processing. And finally, we provide a unified interface for data exploratory, posterior analysis, which I will go over in another slide later, and the backtester, and how we can do the hyperparameter searching. So one of the example of the diagnostic tools is the backtest. It is like a very standard procedure how we like check the performance of the model. So we have this procedure built in the package. You can specify like different settings, such as how you want to split the train and test with like how many folds, how many steps per split, and what is the forecast window, things like that. So this is just one example how we can do the backtest, and we can use this. We can pick different metrics and use the metric to inform the hyperparameter selection. Next, we have this. So we have this backtest procedures built in. We use that in we monitor the performance in a continuous way, such that like in new version developed, and also like when there is a new data coming in the internal data set, we continuously monitor the performance with the backtest modules. So the metric I present here is the estimate, which is a standard metric. And so I conduct a study in 5 data sets, including the external data set like M4 and M3, and also the internal one like the Uber rider, driver, and eater weekly and daily series. So each of these data set contain like from like 20 to 50 time series, and then each of them I do some I do multiple splits, and then estimate the estimate. So each series I will get an estimate. So for each data set, I will have like a series of estimate, and the numbers you see here is the mean of the estimate for each data set. So you can see that our model LGT and DLT does not only like provide flexibility, but also have like up to par performance. It has like a very desirable accuracy compared to some other popular package such as Prophet and Ceremis implement in the model stack package in Python. So as I mentioned, we have this continuous checking day by day. So the way we did it is through a machine learning platform developed by Uber called Michelangelo. It is a appropriately announced platform. So feel free to check out this blog post if you are interested in knowing more how this platform works. So basically, each day we will update the data. Of course, the external data is static, but for internal data, we will have the updates, and then we will train the model with the current version, and then we'll post back to the table in the cloud, and we can like check the results with little human intervention. So a very quick dive into the hands-on. So this is the equation for DLT. I mentioned it in the previous talk. So it is in high level, it is very similar to exponential smoothing the ETS structure, except that we also introduce a regression term, which is very useful for business use cases. And it is implemented in Bayesian style instead of the MLE style in the forecast package now. So we, just like the ETS, we have the forecast equations and update equations. So the way you can deploy this model, train this model and deploy and get the results is pretty straightforward. You just import the library, and you can you have the initialized block, and then you can run the feeds for the train sets and then predict for the test sets. And then you can quickly get your results right away. And you can do the same for other models we support in the current package, such as the classic ETS model, the local global trend model I mentioned in the performance table, and also this dampened local trend model, DLT. And recently we have a new model, kernel time-based regression, KTR. So that is the current gallery of the models. And one highlight for the advantage of using this package is that you have a lot of control on the regression side. So the way you put the regression is you provide the regression column in the data frame, and then you can specify the sign. So for example, if you put a positive sign, that will be the truncated Gaussian distributions from the positive sign. And if it is negative, that will be the truncated Gaussian in the negative sign. If it's equal sign, that is the regular Gaussian distribution. And you can also change the penalty type, like reach and versus lasso. And finally, this is another diagnostic tools I mentioned. You can reintegrate with the Airwix package. So you can check what's the density of the posterior distribution and the convergence status. Just a bunch of highlights, our public exposure of the paper, the GitHub, and other sites and the blog posts. Finally, want to thank you for the team. Without them, we won't have this amazing package so far. Yeah, here is the roadmap. We're running out of time, so want to make a pause here. Any last question here? Looks like there is a bunch. Yeah, I would appreciate if someone like, because there are quite a few messages. If anyone can speak up, I'll be happy to answer the question.
Hi, Edwin. Do you hear me?
Yes.
Okay, great presentation. I was wondering if this orbit can be used to for imputation, for filling missing data.
So this is a time series predictive model. If you are like, you can formulate the question like, if I have the previous information, can I do the prediction for the next step? Or if you're asking if I have missing data in your input, that's a great question. We don't support that currently, but that is yeah, it is totally doable in the package, and
Yeah,
it is in the mobile.
Yeah, because this is like a generative model, right? So
Yeah.
you can use the same model to fill the missing data.
Right. Yeah.
Okay. Thank you.
Okay. I think that's pretty much, we are running out of time, so I'm gonna stop sharing here. And thank you very much for everyone attend the session. See you around.